Hello there, welcome to the A-Level Further Maths video. Here we're looking at modelling with first order differential equations to answer questions from exercise 8a. Now hopefully what you've already done is you've already watched the videos from chapter 7 because we're going to be using those techniques, but we're going to be applying those techniques to mechanics questions. So most of this chapter will be related to mechanics questions. Some of these problems in this section you'll be able to solve using processes you've already seen, but it's important you see the link to differential equations. And remember, there's two different types of ways of solving first order differential equations. You've got the separating the variables technique, and then you've got the integrating factor technique as well. So I'll show you two different examples of solving a first order differential equation in a context. The first question is this one here. A particle P starts from rest at point 0 and moves along a straight line. At time t seconds, the acceleration a meters per second squared of p is given by this formula here, where t is positive. Find the velocity of p at time t seconds. Okay, so if we've got acceleration and we want to find velocity, then we need to recall that there is that link between displacement, velocity, and acceleration, whereby if you differentiate displacement you get velocity, and if you differentiate velocity you get acceleration. So therefore, if we want to go from acceleration to velocity, we're going to need to integrate it with respect to time. So therefore the question here is to integrate this expression up here. So acceleration is a rate of change of velocity with respect to time, so we know that acceleration is the velocity differentiated. So to get back to the velocity, we need to integrate it. So integrate with respect to both sides, and you could think of this as integrating by separating the variables times the dt onto the other side and then differentiate. When you differentiate a derivative, it's just back to v, and then you've got the integral of this expression here. And this expression here is going to be integrated by a little substitution. You may want to rewrite it as 6t to the plus 2 to the power of minus 2. Use a substitution of something like u equals t plus 2. Then you'll have to replace your dt with du, so just make sure you go through that whole process. But then integrate fundamentally, and your answer, however you wish to do it, you may wish to do a kind of reverse chain rule on it as well if you want to, but however you've done it, v is equal to minus 6 over t plus 2 plus c. So there we are, that's the answer for part A. Just to let you know, there's a mistake in the textbook at this point here. I think they use a minus 2 inside the brackets there. This should actually be the question here. Find a velocity of p in terms of t seconds. I think we should be able to now find out what c is equal to, because it says in the question here from rest at a given point t equals 0 starts. So it starts from rest. That's when t equals 0, v equals 0. So let's substitute that in then. T equals 0, v equals 0. And work out what c is equal to. So we've got 0 equals minus 6 over 2, so that'll be minus 3. Move the 3 onto the other side and you get 3 equals c. So therefore your final answer then is going to be v equals minus 6 over t plus 2 plus 3 on the side. So that's our answer for part A. Now let's move on to part B. Show that the displacement of P from O when t equals 6 is given by this expression here. So we want displacement now, so that means we're going to need to integrate again to go from velocity to displacement. So again, let's integrate. So ds by dt, s is representing displacement here, and is equal to what we have here. And now let's integrate with respect to dt. Now the first part of your integral here is going to be integrating by the Lund rule, and then 3 will just integrate to 3t. So let's do that integration then. So it's going to be the Lund rule for this minus 6 over t plus 2. 3 will integrate to 3t, and then we'll have plus c. And we need to show that when t equals 6, we get this expression here, but we need to work out what c is first. Now it starts from a given point O. So in t equals 0, s equals 0. So substitute that in, it's going to be 0 here and 0 here. So it's going to be minus 6 ln 2, and then move that minus 6 ln 2 onto the other side and you get 6 ln 2. So your full relationship then is s equals minus 6 ln t plus 2 plus 3t plus 6 ln 2. The final thing we need to now do with this is plug t equals 6 into this formula. So substitute in t equals 6 then, and we're going to get s equals minus 6 ln 6 plus 2, which is 8, plus 3 times 6 plus 6 times ln 2. What we have to now do is simplify it into this expression here. Now obviously we know where the 18 has come from, but now we need to simplify it all in terms of ln 2. Recall the fact here that 8 is equal to 2 to the power of 3. So it's 2 to the power of 3 here, and then we're going to move that power of 3 to the front as a multiplier. That's one of the rules of logs. So apply a rule of log to get the minus 18 ln 2 at the start, but then group it together with this 6 ln 2 at the back. So that's going to be minus 18 ln 2 and 6 ln 2, and that's going to give you minus 12 ln 2. So it's going to be 18 minus 12 ln 2 equals S, and that's going to be in meters. So there we are, that's the answer for part B, and that's the first question fully complete then. Okay, so let's move on to the next question. A particle P is travelling along a straight line. At time t seconds, the acceleration of particle is given by this expression here. A equals t plus 3 over t, v, where t is positive or equal to 0. So our question is, given that v equals 0 when t equals 2, show that the velocity of the particle at time t seconds is given by the equation v equals ct cubed minus t squared. So this one's a little bit more difficult to the one before because it's got a, t and v in the formula, so we may need to use a more complicated strategy to solve this. So just a reminder, the first thing we need to do in a question like this is convert some of the letters into each other. So a, if you remember me saying that A is velocity differentiated, well that's the first thing I've done. I've replaced acceleration with velocity differentiated, dv by dt. And then what I'm going to do is I'm going to move the 3 over t v onto the other side. So now it looks a little bit like a first order differential equation. It looks a little bit like dy by dx plus py equals q, where y is representing v and x is representing t. There's some function of t in front of the v, and then there's some function of t at the back. So it looks just like a first order differential equation where we of this type of form. And when it's of this type of form, the first thing we need to do is work out an integrating factor. And the integrating factor is e to the integral of p dx, where p is the coefficient of v. So p, in this case, is minus 3 over t, whatever's in front of v. So let's work that out then. So it's going to be the integral of, so e to the integral of minus 3 over t dt, that should be. Integrate it, and we're going to get minus 3 ln t. Then put the minus 3 inside the ln using that rule of powers, and then cancel out the e and the ln, and we get t to the minus 3. So this is our integrating factor. This should all be f of t, beg my pardon. Okay, so now what we do in the second stage of a first order differential equation problem is to now start solving it. The solution is always of this form here. F of xy equals integral of f of xq dx. However, we're not using the letters x and y here, we're using v and t. So it's going to be v, that's the y bit, times t to the minus 3, that's the f of x bit, equals the integral of t, that's the q bit, times t to the minus 3, that's again the f of x bit, dt. So let's now simplify what we've got there, and now integrate. So we get minus t to the minus 1 plus c, and then multiply by t cubed on both sides. That will cancel out the t to the minus 3 on the left. So we get v equals ct cubed minus t. Okay, so the next bit we need to do then is c as a constant to be found. Okay, so we're also told here that v equals 0, t equals 2. So let's plug that in and work out what c is. And then once you've plugged in those two and worked out what c is, you work out that c is a half. So v equals a half t cubed minus t squared. And there we are, that's the answer to this question. Okay, so moving on to the final question. It's a very long one, this one. A storage tank initially contains 1,000 litres of pure water. Liquid is removed from the tank at a constant rate of 30 litres per hour, and a chemical solution is added at a constant rate of 40 litres per hour. The chemical solution contains 4 grams of copper sulfate per litre of water. Given that there are X grams of copper sulfate in the tank after T hours, and that the copper sulfate immediately disperses throughout the tank upon entry, show that the situation can be modelled by the differential equation, and it's going to be dx by dt equals 100 minus 3x over 100 plus t. Okay, so we need to work out where on earth all of these things have come from and give a good explanation as to how we convert this situation into this differential equation. So this is what we're looking to show. Dx by dt here is representing the rate of change of the amount of copper sulfate in the tank every hour. It's the rate at which that's changing by. So we're asked to find the relationship for the rate of change of copper sulfate in the tank. This would depend upon the amount of copper sulfate being added into the tank, as well as the amount leaving the tank, which will have been mixed into the water already. So if we imagine after 3 hours, there'll already be some copper sulfate in the tank, but part of that will be leaving because 40 litres leave the tank per hour. So that will include some of the copper sulfate. So we need to find the relationship for the above. Okay, let's get started. The amount of copper sulfate being added. Well, if we had 40 litres of solution per hour, and then the copper sulfate is 4 grams per litre, then it's going to be 160 grams being added to the tank every hour. And that doesn't that will later on be affected by some leaving. Some of that 160 grams that was added in the first hour will leave in the second hour, but every hour, at least, there will be 160 grams added to the tank per hour. So that's why we have 160 at the front of this equation. Now we need to think about this bit at the back here, which is representing the amount that leaves the tank every hour. So the amount of copper sulfate being lost. We need to know what fraction of the liquid in the tank is made up of copper sulfate. So we need to know how much liquid is in the tank at any given time. The amount of liquid in the tank at any given time starts with 1,000, and then we add 40 litres per hour, so that would be 40 times T. Then 30 leaves the tank every hour. So liquid is removed from the tank at a constant rate of 30, so it's removed at the constant rate of 30, so that's why it's a negative, and added at a rate of 40 litres per hour, so that's why it's 40T as a positive. So this is the amount of solution being added, and that's the amount of solution being removed. So simplifying that, it's 1,000 plus 10T. And since X is being used to represent the amount of copper sulfate in the tank, the fraction of the liquid in the tank that is copper sulfate will be, so X is being used to represent the amount of copper sulfate in the tank, so it's going to be that fraction, X being the amount of copper sulfate in the tank, divided by 1,000 plus 10T. So how do we get the 3 on the top there? So the fraction of copper sulfate in the tank is X over 1,000 plus 10T. Because X, if we go back down here, given that there are X grams of copper sulfate in the tank after T hours, so we know that if we say at 5 hours, we know there are X. We know that X, that's a letter that will change. X will be the amount of copper sulfate in the tank after that many hours. Okay, so X over 1,000 plus 10T is the fraction of copper sulfate in the tank. So the bottom of this fraction is how much liquid is in the tank, and X is the amount of copper sulfate in the tank. But given that we have 30 litres of liquid in the tank that leaves every hour, some of which contains that copper sulfate. So we need to multiply the fraction by 30 to give the amount of in terms of T and X. So the amount of copper sulfate that's lost every hour is the fraction of copper sulfate that's in the tank times 30 litres every hour. So when we multiply those two fractions together, times a factor of 10 on the top and bottom, so cancel out a factor of 10 on the top and bottom, and we have 3x over 100 plus T. So what we've calculated here is the amount of copper sulfate lost per hour, which is the fraction of copper sulfate that's in the tank times how much we want to leave in the tank, so that would be 30 as the multiplier. So the amount of copper sulfate added per hour is 160 grams. The amount of lost copper sulfate per hour is 3x over 100 plus T. So there we are. So the differential equation, the change in the amount of copper sulfate in the tank per hour is dx by dt equals the amount added, take away the amounts lost per hour. So it's going to be 160 minus 3t over 100 plus t. And these questions here are actually becoming more popular in the further maths exam at the moment. So make sure that you've understood this, maybe go back and rewatch it again, but then have a go at these types of questions in exercise 8a, please. Okay, so amount added, take away the amount lost. Okay, so now that we've got the equation, let's go ahead and solve the equation. So the question here is, find the number of grams of copper sulfate in the tank after 6 hours. So the differential looks like this. It's dx by dt equals 160 minus 3x over 100 plus x. Now we could move all the t's onto one side or the x's onto another and then solve the derivative that way, but it doesn't look like you'll be able to do that. What we'll have to do here is move the 3x over 100 plus t onto the other side and then solve it like we would a dy by dx plus py equals q derivative, where we need to use an integrating factor and p is the function that's in front of the dependent variable. So p is therefore positive 3 over 100 plus t. So let's now work out what the integrating factor is going to be. The integrating factor is always of the form e to the integral p dx, or t, depending upon what your independent variable is. So e to the integral of 3 over 100 plus t dt. Let's now integrate that power. So that's going to be 3 ln 100 plus t. Move the 3 in as a power on the ln, and then cancel out the e and the ln, and we'll get f of t is 100 plus t all cubed. Now that we've got the integrating factor, we can now go for the solution, and the solution is always of this form. The integrating factor times y, or in this case it's going to be x, equals the integral of the integrating factor times q, and that's the function on the other side of the integral. So this is what the next stage looks like. It's going to be x times 100 plus t all cubed equals the integral of 160 times 100 plus t cubed dt. Next thing we'll need to do then is we'll need to integrate the right hand side. You could use a substitution of u equals 100 plus t if you wish to do so. That will lead you to 40 because you'll need to divide by 4 on the 160, and then you increase the power by 1, so it's 100 plus t to the power of 4 plus c. And if we were to then cancel out the 100 plus t's cubed on the left hand side, we'll be left with this: x equals 40 times 100 plus t plus c over 100 plus t all cubed. So what we're told in the question is initially there's no copper sulfate in the tank, so at time t equals 0 x equals 0. So let's plug that in and work out what c is, and c is going to be minus 4 billion. So minus 4 billion is the value for c. Never had such a big value of c before. And now we need to just plug in the value for t equals 6 to find out what x is, and do the calculations. We get 882 grams. So there we are. That's how many grams of copper sulfate are in the tank after 6 hours. Right, and move on to the final part. Quick part here. Suggest a possible refinement for the model. The model could be refined so that the copper sulfate does not immediately disperse upon entering the tank, which is unrealistic. Generally, the copper sulfate would cluster in certain areas rather than disperse throughout the tank uniformly, because when it comes out of the tank, it's going to come out uniformly. Rather, it's to do with it coming out of the tank. Okay, let's move on to a question for you to have a go at then. This is question 4 from page 174. Pause the video and give this question a go. Okay, so let's have a go at question 4 then. A particle P is moving along the x-axis. At time t seconds, the displacement of the particle from O is x centimeters and its velocity is v meters per second, where v equals e to the minus x over 2. Given that the particle is initially at the origin, find x as a function of t. So the first thing we need to consider is that when you differentiate x, you get v. When you differentiate v, you get a. We don't need the second bit, but the first bit's important because v is x differentiated. So it's going to be dx by dt equals e to the minus x over 2. Now it's a first order differential equation, but it's not the one where p and q are involved, where we have to do an integrating factor. It's one where we just have to move everything onto the correct side and then integrate it correctly. So I'm going to multiply by e to the x over 2 onto the left hand side, leave dx where it is, and multiply by dt up onto the right hand side, effectively leaving behind a 1. Then we can integrate both sides just like that, and then on the left hand side it's going to be 2 e to the x over 2 equals t plus c. Now at this point I'm going to work out c because it looks simpler, and then I'll rearrange it to get x equals. So it says given that the particle initially is at the origin, so that means when t equals 0, x equals 0. So set x equal to 0, that's going to make it e to the 0, which is 1, times it by 2, you get 2. So t is 0, so c equals 2. So this is going to equal then 2e to the x over 2 equals t plus 2. And now we have to rearrange this to make it x the subject. So divide both sides by 2, so it would be half t plus 1. Then we get rid of the e by learning both sides, so x over 2 equals ln half t plus 1. And then times everything by 2, so it's going to be x equals 2 ln half t plus 1. And there's not many ways that we could probably simplify that anymore. We could move the 2 in as a square, but not much else can be done there. So there we are, that's an expression for x as a function of t. So there we are, that's all we're going to go through in this video then. That's exercise 8a. Have a go at plenty of the questions from that exercise, the problem solving ones, the exam style questions. These are a fan favourite of the exam board at the moment, so make sure you have plenty of goes of those wordy questions, because that's how they're going to examine the first order and second order differential equation content inside a wordy question. So make sure you're good at them, and where you get good at them is by practicing the questions. Thanks very much for watching, everyone.